No problem. I'm going to intro Wim. Is that all right, Kay?
Yeah, it's
We're unmuted. We're ready to go.
Okay. Thanks for your patience. We got everyone assembled. I'm here to present Nimo for his thesis defense. Nimo, as many of you know, has been here for a while. He actually was an REU student with us in summer of 2017.
Yep.
In the very beginning of the Penrose system, and we were really glad to have him stay on to do his PhD with us. He's done a lot of amazing work, many pieces of which are not actually talked about in the thing you're going to hear about today. But today he's going to talk about three really great papers, one of which was at SIGGRAPH, one of which was at CHI, and one which is at Learning at Scale, all of which were really excitingly received. So I hope you'll be excited to hear all this good research about authoring conceptual diagrams by codifying visual representations. Take it away, Nimo.
Thank you so much. Well, wow, today is the day. We almost filled the room. Thank you so much for coming. So let's talk about diagrams. Well, diagrams are visual representation of ideas. We see them in textbooks, academic papers, blog posts, and YouTube videos all the time. People use them to learn, teach, and communicate important concepts to each other. Diagrams are really useful. Experts use diagrams to work on tough problems. In 1945, a French mathematician sent letters to 100 mathematicians and physicists to ask them how they do their thing. And letters came back, and many of them said they draw diagrams or use mental imageries when solving problems. And those who are not experts also benefit from diagrams too. Learning sciences say that people learn better from words and pictures than words alone. And this has been repeatedly shown to be true in past research. And they even made it a principle for teachers, what's called a multimedia principle. So diagrams are great, so let's just make a diagram. So this is a diagram of the Lewis structure of the sulfuric acid molecule. So what I want you to do now is open your favorite drawing tool and then just make this diagram and raise your hand whenever you're ready, okay? And meanwhile, I'm gonna show myself making this diagram earlier in Figma. Throughout my PhD, I spent quite some time diagramming in Figma. I've probably done hundreds, if not thousands, of these diagrams in the past 6 years, so I should be an expert. Let's see what I can do. Look, an atom, another one, a lining, a round atom. 10 seconds in, I'm making great progress. Well, the truth is I'm actually pretty slow, and so I'm gonna play this in 10x. So I guess I'm not getting a PhD in Figma after all. Seriously though, look at what I'm doing right now, and notice that I'm constantly moving things around, checking alignment, and changing sizes and so forth. These are a lot of low-level operations. And the issue here is that I know what I need to draw. I have the picture in my head. It's just the executing of the diagramming that's time-consuming and annoying. So in a sense, things are not aligned, both figuratively and literally on the screen. Even after all this time, my bonds are still off. So let's try a more realistic setup. Has anybody, is it already done? Has anybody finished their diagram on their thing? No? No raised hands? I figured. So let's try a more realistic setup. Say you're creating a quiz with these diagrammatic problems. And something you will see in the textbook quite often, one problem has 4 diagrams. And let's say we're making 3 of these problems, so we're making 9 diagrams for 3 problems. And I just did the 1 correct diagram. So how bad is it to make the rest of them? Well, not much faster. Now I'm playing this in 20x. Although I can copy paste stuff, the annoying bit is that I still need to move these shapes around quite a lot. And the other thing is, in a sense, the more I diagram, the worse it gets. let's say if I'm not happy with my double bonds being this far apart, the more diagrams I've already made, the worse it gets because I have to change every single one of them. Okay, that's enough of me suffering to see, but you get the point. The point is diagramming is a lot of manual work. And educators actually agree with this. So in past interviews with teachers, they say that diagramming is too much work and annoying. Diagramming is mostly copy pasting for me. It's really hard to create simple shapes by myself. And quite often I hear this, diagramming is painful with current tools. So in this talk, I'll show this issue of tool support for diagrammers and show you some work that I've done in the past few years to improve this situation. So the thesis statement for my dissertation is the following. New diagramming tools that codify visual representations support educational content authors in creating quality diagrammatic problems much more efficiently. In part one of the talk, I will talk about an interview study that studies how experts in different domains create diagrams and highlight the concept of visual representations and their role in the diagramming process. In part two, I will introduce Penrose, a new diagramming tool, newish, I'm not that old, but a new diagramming tool that codifies visual representations. I'll show how it allows this codification and capabilities it enables in diagramming. And in part three, I will revisit our motivating example and present Edgeworth, a tool that is built atop Penrose that directly supports educational content authors to create diagrammatic problems like the ones we saw. So in this part, I will present what's called a need finding study, where we investigate how people create diagrams using current tools right now and how these tools support their diagramming process. And the goal is to help inform the design of future tools. And the results came from a Kai 2020 paper. For the purpose of today's talk, we will zoom in on one particular aspect, the idea of visual representations and how tools fail to support them. So a core activity of diagramming is in designing good visual representations. What do I mean by that? I'll use an example from a seminal paper, why a diagram is sometimes worth 10,000 words to illustrate what I mean. So now consider a truck moving rightward on the screen and think about the forces that are exerted to car B and how you will visualize it. Okay, so a standard representation here, you've probably seen it in physics classes already, is what's called a free body diagram, where car B is represented as a mass point and the forces are represented as arrows with directions and magnitudes. And now I have two additional diagrams representing the same thing. They're kind of less standard. So the circle diagram shows the magnitude of the force, but loses the directionality of the forces. And the chocolate bar one, I just came up with it and nobody will understand it unless I really explain it this way. So this kind of, the point is this mapping from ideas such as forces with directions and magnitude to visual elements like arrows, points, and the directions of the arrows is visual representation and is a big part of diagramming to design good ones. So how do experts design their diagrams to visually represent ideas? The results I will talk about came from interviews with 18 diagrammers from 12 different domains. They range from architecture to K-12 education to advanced math research. So like the free body diagrams, there are often standards in the field. Our participants reported the process of surveying representations in their domains. For example, in computer graphics, the view angle or the camera is often represented as these icons of eyes. And then the lights are represented as literal visual lines bouncing in the scene. While allowing personal style for their content, diagrammers prefer to stick with the conventions if there are any. And in the absence of existing standards, some diagrammers create their own ones, like these diagrams showing the structure of mathematical groups created by one of our participants for a new book that they're working on. And P1 describes it as turning something that has never been seen before into illustrative diagrams. And this process is therefore very creative. And people are often quite iterative in their design. For example, one participant evolved the design of the visualization of this projector calibration system over time. And to make better visual representation of the system, they experimented with all kinds of styles of labels, lines, arrows, and so forth, to denote more complex configurations. So now we learned it's a complex process to iterate on these designs of visual representations. So participants prefer to keep them around when they have one. So now here's the problem. We found that diagrammers use ad hoc solutions outside of their tool to keep representations around. And let me show you some examples. Here, one participant keeps versions as separate artboards in Adobe Illustrator. And it's a kind of a tree of all the past design decisions they've ever made. And they also include different ways of visualizing the same object. Here, other diagrammers try to maintain visual consistency, like the color of the orange and the line width, across their work but what they do is they keep a separate text file with low-level parameters like the color code and the line width because their tools don't usually remember them. And others curate a library of all the diagrams they've ever made such that they can build on top of them whenever they want to make a new one. And in this case, it's a giant overleaf document with all kinds of TXT diagrams. Okay, so the diagrammers who know how to program will sometimes try to program their diagrams by encoding components of a diagram as macros or functions. Here's an example of macros in LaTeX, and unfortunately, they are pretty brittle. Like P11 said, macros are terrible. I make macros that are 20 or 30 braces deep, and they are just incredibly hard to write and edit. And these ad hoc solutions exist because the tools don't let them encode visual representations. And one reason why diagrammers are keeping these numbers around and copying canvases is because of the high cost of making changes to their diagrams. So like P1 said, when you already have a diagram and all of a sudden you think of a way that you want your diagram to be different, it really shouldn't involve starting all over again. And instead, you should just tell the tool to start it over. And this is what I mean by codifying visual representations in digital tools. And the tool should really remember how ideas are translated to visuals and help experts keep track of this translation so they can easily be reused and tweaked later. So let's talk about, in the next part of the talk, let's talk about a tool that does just that. And in this part, I will introduce you to Penrose. Penrose is a diagramming system that is designed to codify visual representations. And to talk about Penrose, I have to wear my Penrose jacket. Okay, now we are properly ready to talk about Penrose. Okay, so a bit about Penrose first. As many of you know, Penrose is something, like Josh said, Penrose is something that I've continuously worked on since 2017. Penrose first appeared as a SIGGRAPH 2020 paper, and there are many cool aspects of the system that you talk about that I won't have time to get into, unfortunately. But meanwhile, feel free to visit the site to check out some live demos. For this dissertation, Penrose is both an important basis for this dissertation, but also outside of the dissertation is an open source project that I'm very, very passionate about. So let's talk about the main idea behind it. The main idea behind Penrose is to encode the mapping from abstract and mathematical object to visual objects and visual relationships. And I will show you that this encoding allows Penrose to make this mapping reusable over a range of concepts. So let's just use a simple diagram to show you the core design. Let's make a diagram about two sets, A and B, where B is a subset of A. These are called Euler diagrams. They're not really Venn diagrams. Some people are very nitpicky about this. So let's make an Euler diagram where B is a subset of A. And in Penrose, a diagram is a trio of three programs. First, what does the diagram illustrate? The substance program is a declarative notation that contains the content of the diagram. In this case, there are two sets, and set B is a subset of A. Now, the substance language itself is defined by another language that says what can be in substance, the domain language. Here, the domain says there exists a type of object called sets, and sets can relate to each other in certain ways. So here we have a predicate that says one set can be a subset of another. You can think of them as kind of there exist sets and then there are facts about them. So subset is one of those facts. Now that we have the objects and the relations, what do they look like? And style is a style sheet language that maps from logical entities to visual shapes and these abstract relations to high-level graphical constraints. So let me switch to the Penrose editor and walk you through the style for the Euler diagrams line by line. I've commented out everything but these outer blocks in style. So here, the for all before the block is what we call a selector. They let us say things like all sets are represented as circle. On commenting lines 7 and 9, now we will have two circles for the sets. And notice that Penrose doesn't really force you to say how big the circles are and where they are, what colors they have. Penrose will in fact initialize the properties with defaults if left unspecified. So there's a button that says resample to the top right. This resample button actually lets you cycle through different initializations of these properties that we talk about. Okay. So if you like a specific value for something like the fill color for the circles, you can specify this in the block. So for example, if I want to make the fill color this very specific purple, then I can do this. And the properties for each shape type like circle are available on our official documentation. And also inside of the editor itself, if you just hover on the name of the shape in the shape constructor. And remember we had these labels on the sets, A and B on top of the circles. How does that work? So basically we can create a shape of the equation type for each set. And if we just uncomment this, we get some text, but they're clearly not the right ones. So to make this right, I will ask you to move over to Substance and notice line 7 that says auto label all. So what it does is they basically populate this dot label field that is associated with the substance object with the string value of the identifier. So for set B and A, the B dot label will become B, A dot label will become A. And assigning this label field, line 11 in the style program to the string property of the equation will basically get you labels that say, A and B. So now the labels are outside of the circles. And if you remember the diagram, we want them to be inside of their corresponding circles. And here on line 13, we have this statement that says ensure. And uncommenting it will basically ensure that x.shape, the circle, always contains x.text, the equation. And ensure is what we call a constraint. It is a visual relationship that Penrose must hold true at all times. And notice how if I click resample, notice how the labels will always be in the right place. Despite different initializations. So now, substance also say on line 2 that B is a subset of A, but our diagram is not reflecting it. So what we do is to write another selector to handle this. You can simply select the object that satisfy the relationships. Let me highlight this again. So you can simply just select the object that satisfy relationships like subset by adding a where clause right after the for all. So here, what we want is for all the subsets, we want the superset circle to contain the subset circle, right? So let's just uncomment that. And now, the subsets will always be inside of the superset circle. Okay, so one other thing is notice on the right here that the label for set A is poking into the subset a little bit. This might cause some ambiguity down the line. So we actually don't want that. We want to tell Penrose to not let this happen. So what you can do is to ensure the label of the superset is always outside of the subset by adding another constraint that says to ensure the text and the shape and the circle to be disjoint, visually disjoint from each other. So on commenting this, we'll make sure that the label is always outside of the subset. So okay, after all this work, we have a bunch of diagrams for B subset A. But the power of Penrose is that you can now change the substance and the style will continue to work. And here I'm adding some statements and running Penrose as I go. And you see that the subset relations are always handled correctly. And the other thing is for each change that I just made, the resample button will continue to work. So every time you make a change to the substance, you get many, many diagrams for free. And in short, style specifies the visual representation of substance as a set of constraints. And it's the job of the Penrose layout engine to solve for some solution. So here we use standard techniques from computer graphics to translate the constraints into an energy function and basically run an algorithm that is basically like gradient descent to solve for solutions. And our team has done a lot of work to make the constraint solving fast and reliable, but I unfortunately won't have time to get into it today. So following the same process that we saw for these set Euler diagrams, one can build other domains by writing new domain and style programs. So this is the domain program for these chemical molecule diagrams that we just saw. And we can encode elements like atoms and bonds and the number of valence electrons in the domain program. And the style is a bit too long to show, but the principle is very similar to what you saw in the demo. And with one style file and one domain file, you can now write substance programs and create diagrams for new molecules. And similarly, the geometry domain can also be created this way, and it's probably our largest domain by far. And the main constructs in the domain will still kind of fit on the same slide, which I think is pretty cool. So instead of showing you example diagrams, I'm just gonna show you me pasting some substance programs into the editor. And notice that I'm not making any changes to style and domain. Penrose will just lay out the diagrams whenever there's a change to the substance. And both of these domains, the molecules and these Euclidean geometry diagrams, will be very useful in the next part of the talk. Okay, so over the years, many more diagrams were made this way using Penrose. Here's a screenshot of our online gallery, and these diagrams are both made by us, like the ones you saw, or and people in the open source community. And throughout my PhD, me and I and the Penrose team put a lot of time and energy in building and supporting this open source community. We've written many docs pages, built a Discord community now with 400 plus members, and accumulated a lot of developer docs in the form of GitHub issues and PRs. And this is something I'm passionate about, and I feel very lucky that many people have seen and made diagrams with Penrose already. So one really cool use case of Penrose to me is the integration with other open source tools. So the lean theorem prover, a lot of CMU folks also work on that, now includes a Penrose generated diagrams in their VS Code extension to help visualize proofs in various domains. So to recap, Penrose is a new diagramming tool that codifies visual representations as style and domain programs. Once codified, representations can be reused for a wide range of content in different domains. And there are a lot of things that we want to learn about Penrose but didn't get to. For example, what are some generalizable strategies to build robust style programs that will work for all possible substance programs? How to design the domain so people can pick up a new domain really quickly. And some domains have similar shape constructions, constraints, or bigger components. How to reuse and compose these components across the domains, and many, many more questions. But what we'll attempt to answer today is this question: what is Penrose's potential for scaling up diagram production for a specific application domain? You might ask, which domain? Remember this. Let's talk about diagrammatic problems. So next, we will zoom into one specific use case of this idea of codifying visual representation, and talk about using this codification to generate diagrammatic problems for educational content authors. And we recently published Edgeworth at Learning at Scale 2024. So the content for this part contains both things from that paper and also some original content. Specifically in this work, we look at a very useful problem type that involves a lot of diagrams. And here are two examples. On the left is matching a plot of a linear function to its formula. And on the right is matching an assertion that two triangles are congruent to actual geometry diagrams. And the cognitive scientists in past research found these so-called translation problems to be effective for improving students' visual fluency. And by fluency, I mean the ability to correctly map among words, symbols, and diagrams. And when students fail to map, let's say, if they lack fluency, and they fail to map symbols to diagram, the diagram can't really help them solve a problem because that's the wrong diagram. And the power of these translation problems is in this repeated contrasting cases of the mapping, let's say between symbols and visuals. And effective practice using translation problems will involve a lot of diagrams that are correct, incorrect, and anywhere in between. And the students will slowly make sense of what's a correct mapping through practice. But that's a lot of diagrams. And in this part, we aim to leverage what we've built in Penrose to address the demand for these diagram variations. This is a correct answer we saw about triangle congruence. What does it take to, say, get an alternate correct diagram that shows two congruent triangles by using different theorems? We know that we can express the essential content, what's being illustrated in this diagram using substance, like what I'm showing here. Now, changing one pair of the equal segments to another pair will give us another setup where the two triangles are congruent. While this might be quite a visual change if you are moving them around in the visual editor, the change to substance is literally just that one last line. And in fact, you can do this to get all kinds of diagram variations. with very small changes to the substance program. So like this alternate correct answer that we just saw, we can also delete one statement and add another to make an incorrect diagram. We can also just delete 3 statements and get another incorrect diagram. So again, this is our intuition. We have a very concise notation for the essential substance, pun intended, for a diagram. And Penrose will automate the layout whenever the content of the substance change. So the idea here is to automatically generate a lot of diagrams, so teachers don't have to make them by hand. So what we want to automate are these small edits to the substance programs. And researchers sometimes call these randomized edits mutations, almost like genetic mutations to a program. So what kind of mutations are there? The simple operations like adding and deleting statements are pretty straightforward. You pick a statement at random and just do the addition or deletion. What's interesting is in edit. Theoretically, you can call the combination of a delete and an add an edit. But what we found empirically are 3 kinds of edits that work well. So these are replacing the arguments with some existing variables, swapping the arguments around, and also keeping the arguments the same while replacing the name of the function. You may ask, how do you know which function to pick? Conveniently, we have this other language called domain, which tell you exactly what's possible to write in the domain and tell you what types are the arguments in the domain program. So this is the idea behind Edgeworth. We call it problem authoring by diagram mutant selection. Where the way people will use Edgeworth is that they first write one substance program and then feed it into Edgeworth. Edgeworth performs mutations on the program to get mutants of the diagram and present it in the user interface, and the user simply selects desirable diagrams from that pool of diagram mutants. And by combining them, they can make translation problems. Okay, so remember this example. So let's do it again using Edgeworth. So first, I make the diagram in Penrose, and you've actually seen it in the last part. Let's now that we have the one diagram, let's try to make a problem. Let's just make what's on the left 3 incorrect diagrams along with the correct one. So what I do is I copy the substance program over from the Penrose editor, paste it into Edgeworth, and then click generate variations. Now I will get both my original correct diagram and a grid full of variations to that diagram. The first diagram is corresponding to my input, and the layout is a little weird, but the standard Penrose tricks apply. I can just hit resample and get another layout. Well, now all I need to do is to go through the diagram variations and select the diagrams that I want from this grid of variations. So my goal here is to find 3 incorrect answers and put it together with the correct one, and we have a problem. Okay, so now that I'm done with my selection, clicking show problem will give me a preview of the problem and the answer. And after this, Edgeworth lets you export the diagrams to include in the problem set. Say if you are working on a PDF that you will print out, you can reuse the diagrams that way. I'm done. Like, this didn't involve dragging things around at all. Well, so how well does Edgeworth work? To evaluate Edgeworth, we ask 3 research questions. Number 1, is this approach, random mutation, reliable? Because we're performing them at random, even if they type check, they might produce wacky diagrams. So can Edgeworth reliably generate suitable diagrams for translation problems with relatively few variations required? Second, are people more efficient when using Edgeworth? So the question here will be, comparing with the conventional drawing tool, are authors more efficient at making translation problems using Edgeworth? And last but not least, is Edgeworth actually useful? Do real-world instructors consider Edgeworth generated translation problems to be useful? So before we go into the evaluation studies, we needed some materials to run the study. So we collected a data set of translation problems from textbooks and online classes in geometry here. Also these graph-related problems from a discrete math textbook, and also these Lewis structure diagrams from a online course on General Chemistry 1. And in total, the data set contains 31 problems. So let's go into the first study. We want to test if Edgeworth mutation-based approach can reliably generate diagrams that can form a valid translation problem. So here what I mean is 1 correct answer and 3 incorrect answer diagrams with relatively small number of mutants. And we have decided the relatively small number to be 10. Because this is what the user typically sees on the screen the first time to generate the variations. So to evaluate this, we generated 10 diagrams for all 31 problems that we collected in the problem set, so 310 in total. And a colleague and I counted how many of them are correct answers to the problem prompt, incorrect, or visually unreadable. So there are 3 categories. Overall, for out of these 31 problems, we found that within 10 mutants or variations, Edgeworth can generate enough diagrams. So this means 1 correct, 3 incorrect to be used to form translation problems. And for the ones that failed, we ran another batch of these mutants. So within 20 mutants, 30 out of 31 of them are, can produce enough diagrams. So to make sure, like our rating is reasonable, the colleague and I sampled 20% of the data set and then compared our codes to each other and found a perfect agreement. So Cohen's kappa equals 1 for this sample. Okay, so on to the second question. We designed an experiment to test if people are efficient at creating problems when compared with a baseline. And here we've decided that the baseline is Google Drawings because it's somewhat representative of a WYSIWYG drawing tool, and most of the people have background using them in the past. So for this study, we recruited 16 undergraduate and graduate students. They all have backgrounds in chemistry and geometry, and they're divided into 2 groups. And participants are given 2 textual prompts, 2 textual prompts of translation problems. And for each prompt, there's a corresponding static PNG diagram of a correct answer to the prompt. And what they do is they make diagrams for each prompt twice using both Edgeworth and Google Drawings. And the ordering of these tools are counterbalanced. What do I mean by that? Let's just take the geometry group of 8 people as an example. So these 8 people represented as green circles are further split into 2 subgroups. And 4 of them will always use Edgeworth first, and the other 4 will always use Google Drawings first. And the 8 chemistry participants also have the same arrangement. So let's see what the 4 geometry Edgeworth first participants will do on their first problem prompt to understand what will happen in the typical study session. So to get started, every participant is given an example program in both Google Drawings and Penrose. And what's in the example basically covers all the construct they will need in the subsequent tasks. And then they're given the first prompt, right? So first, they will spend they will spend the first 10 minutes, up to 10 minutes, using Penrose to reproduce the correct diagram they're given. So if they're done with the diagram early, we move on. But if they can't finish a diagram, we will give them one. So after this, they have one correct diagram, right? After this, in the next up to 10 minutes, they're asked to make up to 10 incorrect diagrams by basically putting, in this case, we're using Edgeworth. So as you saw, putting the correct diagram in Edgeworth and then generate variations and select 10 that they want within up to 10 minutes. If they finish early, we also move on. So in total, they can spend up to 20 minutes to produce 11 diagrams, 1 correct, 10 incorrect, at most. So they will also repeat this process in Google Drawings for the same prompt again. And we will, and we record throughout the study session, we will record how much time they took for each diagram they made. And all of these sessions are structured this way. So 2 prompts, 4 tasks, and only the domain of the prompts, chemistry or geometry, or the ordering of the tools, Edgeworth first or Google Drawing first, will change. Okay, so here are some task completion data. For chemistry, everybody get the correct diagram in time using both tools. And one could have finished 10 diagrams in 10 minutes using Google Drawings. For geometry, 3 couldn't complete the substance programs for at least one of the prompts. And all made 1 correct diagram in time with Google Drawings. However, 6 out of 8 participants couldn't finish 10 diagrams in 10 minutes using Google Drawings for the incorrect part of the geometry group, where while they all succeed using Edgeworth. Now onto some timing results. So taken together, participants are roughly 2 to 2.5 times faster when using Edgeworth to produce the translation problems. And the speed gain is especially big when making incorrect diagrams, where Edgeworth is 3 to 4 times faster. To test the statistical significance of the result, we ran a 2-way repeated measures ANOVA and saw that the results are indeed statistically significant. And for the correct diagrams, the results are kind of mixed, likely due to the kind of upfront cost of having to make the first substance program. And quite notably, you will see that participants are actually faster when using Penrose to write the first correct diagram in chemistry, but they're slower in geometry. And this is likely, you saw the domain programs, because geometry is a much more complex domain, and substance is a bit harder to write. Okay, so to answer the third question about its usefulness and really the sort of ecological validity, is it useful to the target audience in the real world? We recruited 9 expert educators, and for each of them, we will sample 2 to 4 translation problems from the translation problem data set. And we will show them the textual prompt of the problem and give them the substance program. And then they will start using Edgeworth to generate diagram variations. And then they will assemble a problem or 2 based on their preferences. And during the session, we will ask them for qualitative feedback on how well Edgeworth worked for them, and also the problems they've generated in this process using Edgeworth. And several kind of high-level points I want to highlight from the study. First, they all indicated that we use the problems that Edgeworth generated in the session, and they want to use them in places like warm-up quizzes in the class, in-class activities, these clicker questions, and even suggested asking students to make problems using Edgeworth as kind of a educational activity to make problems themselves. They also like that they can do recognition over recall when using Edgeworth. So each who said here that Edgeworth can come up with different possibilities than the ones that would be immediately apparent to me. Interestingly, when we asked them what makes a good problem, they actually said different things. One example would be this question of what's a good incorrect answer. And some people some experts really prefer super tough distractors that are like very subtly different from the correct answer, while others prefer a more balanced mix of some things that are very obvious and then one or two distractors for the student. So really there's kind of a diverse set of standards among the experts. So one thing that we were concerned about and asked them is this occurrence of duplicated substance programs that might happen at random because Edgeworth performed these random mutations, right? They might swap an argument, they swap two arguments and swap it back. Then you basically will get duplicated programs. It doesn't provide any guarantees for that. And to our surprise, they actually liked these what's called isomorphic diagrams, the diagrams that have the same content but different layouts, because we randomized the diagram layout in Edgeworth. They actually kind of like it because they prefer the students to see the same thing kind of from different angle, if that makes any sense. So this we were pleasantly surprised by that. Okay. So now, let me conclude the talk by walking over a thesis statement again. In part one, we learned how important visual representations are to the diagrammers. In an interview study, we discussed how tools fail to support them, resulting in diagrammers inventing ad hoc solutions to keep track of their representations. These results prompted the design of Penrose, a diagramming tool that is designed from the ground up to codify visual representations. And I show you how the three languages in Penrose work, especially the style language, which maps from abstract object to visual relations. And using this codification, Penrose can automatically lay out diagrams in a domain without the need for low-level operations, like we saw in the motivating example. And finally, Edgeworth is an application of Penrose in the domain of diagrammatic problem authoring. Educators have this demand for more diagrams to improve their students' visual fluency, and we designed Edgeworth to automate the authoring of diagrammatic problems. And in a series of evaluation studies, we found that Edgeworth reliably generate diagrams suitable for making a four-choice, multiple-choice diagrammatic translation problems within 10 to 20 mutants. And when compared with the WYSIWYG tool, in this case Google Drawings, authors are 2 to 2.5x more efficient at creating translation problems. And finally, in the demonstration walkthrough study, experts found Edgeworth generated problems to be useful for their teaching. So I will quickly mention two areas of future work to conclude this talk. First, Edgeworth's current approach is to delegate the decision of diagram selection to the author completely. While it's already saving time for the authors, I believe there are some opportunities to let authors express their quality preferences. So for example, for the expert that wants more distractors, might want to tell the tool, give me more distractors, harder distractors, more edge cases, and so on. And this will require some level of domain knowledge in the tool. The tool need to know what's a tough answer. So obviously, we know that large language models have this some level of domain knowledge from their vast training set, and but they include the visual representation in this strange fuzzy way. So the diagrams using pre-trained models, the diagrams generated out of the box usually are pretty bad in terms of visual quality. I believe, however, our encoding of domain-specific concepts and visual representations can help build a bridge between pre-trained LLMs and authors who want to use natural language to diagram. And we've done some experiments on this front, but there are a lot more to be done in training and tuning models that have better visual capabilities, and also building agents that interact with diagramming tools like Penrose, better. So the second area I'm excited about is to extend Penrose's approach to support interactive diagrams. They are another application area that I think can benefit from some automation. And the specific advantage of Penrose here is that it's declarative interface to specify shape relations. And quite often, these interactive diagram authors are basically doing that, but with manual programming. And the difference here is that Penrose has a layout optimizer, and it knows exactly what to do when the diagram changes. So this is what I like to call semantic preserving interaction. And we've already done some preliminary work this summer to experiment with it in Penrose itself, which you saw, that was a live demo, as well as a newly released this week TypeScript API called Bloom. So check it out on the Penrose website. Okay, so now we're at the fun part of the talk. Okay, so this thesis defense is brought to you by Brilliant.org, my future employer. And the online learning platform that lets you master math science and computer science through fun hands-on problem solving with Brilliant's interactive approach, you learn by doing, proven to be 6 times more effective than traditional methods. Whether you want to dive into advanced math, explore programming, or understand the wonders of physics, Brilliant's bite-sized lessons and engaging challenges make complex concepts easy to grasp. Start your learning journey today and transform how you think about learning using my code Dr. Nimo, D-R-N-I-M-O. Again, that is Dr. Nimo, D-R-N-I-M-O. And visit Brilliant.org to get started and unlock your potential.
It's a great podcast voice.
Obviously, I'm not a doctor yet. I don't have the code. But I figure I should do it. So I'm trying not to be too sentimental because I'll be around and it will be really awkward. But they're like, I'll be around for a couple of weeks. So I would like to thank a couple of people. First and foremost, my advisors, Ken and Josh. Well, thank you for the past 6 years of collaboration and guidance. You made me a better researcher, and yeah, it was a fun journey. And like Josh said, this is young versions of us, probably like 100-pound lighter when combined. So this is us at the end of the 2017 summer REU program. I remember that summer really fondly. I was very productive. I was a kind of excited undergrad student working on this fun diagram project that I never heard of. And in many ways, the PhD kind of felt like an extended, summer for me. That was a lot of fun. And I would like to thank my advisors for making it possible. You are my patron because you're paying for my. And obviously my committee members. Well, thank you for being here and giving me feedback on my dissertation. And the group of people that I work with the most, the Penrose team. Many of you are here today, and some of you are online. And also the open source community we've built up over the years. And you guys keep me going on solving this problem of diagramming. Initially, it was a cool coding project that I enjoy, but now I'm deeply convinced that this is an impactful and important problem that I would like to do something about. Next are the PhD friends and colleagues over the years. I don't really like photos, so I found these two. But if you're not pictured, please don't feel offended. I will make sure that I include your name in my acknowledgement section in the actual dissertation document. So the next thing, so about like what half of the CMU pool club is in this very room right now. So I am known to spend a lot of time with these rounded objects. I make them disappear. I make them go boom. Check out this break. Oh, and I make them go boom, and it's the actual thing that kept me going throughout the year. So we were talking about diagrams, and I made some pool diagrams in Penrose, and I feel obligated to do that. And next, mom and dad. Believe it or not, the last time I saw them was before COVID. So it's been a long time. The last time I saw them, I was a young PhD student, and now I'm graduating. It's late night right now, so they're not really on the call. They will see the recording of this. Try not to get too sentimental, but I feel very lucky to have them. And in this very room right now, Dr. Reese, my girlfriend, and she became a doctor last year, something like that. So hopefully very soon we will be equally educated. Now I'm less. And also featured in this photo, you might see this this cat, right? This animal. You sat through 15 minutes of this. I gotta show you the cat pictures. So follow him on Instagram. Yeah, that's it.